Hi, we are Nick and Antonia from Rescribe. Welcome to our practical guide to optical character recognition. The whole course is split into 5 parts. This first bit here gives an overview of the technology. The second, an introduction to using the command line on your computer. The third will teach you how to download and run Tesseract, an open source OCR program. And the fourth will give some tips for best results. The last part will introduce an open source one-stop shop OCR solution using Tesseract with optimized pre-processing. If you have very little time, you can simply watch part 2 and part 5. This will give you a quick introduction to the command line and the instructions for how to use an all-in-one OCR tool on your own laptop. However, we would recommend watching the whole course in order to get a bit more background knowledge on the technology, the software, and tips for good practice. In this first section here, we will start with a brutally short history of optical character recognition, otherwise known as OCR. Briefly said, optical character recognition is the technology that can convert digital images of printed, handwritten, or photographed text into machine-readable files. These converted documents can be processed by computers, meaning they can be searched, edited, and analyzed. Just think of the advantages of a searchable PDF over one you cannot search, just to illustrate why the technology is useful for academic purposes too. The technology itself has been around for surprisingly long. Its conceptual origin relies with the optophone, first invented in 1913 by a Frenchman, and designed to convert printed text into acoustic signals as a reading aid to visually impaired people. Although the optophone did not really take off, the same purpose served as primal inspiration for the first inklings of modern OCR. In the 1970s, Ray Kurzweil developed a technology recognizing text in virtually any font, and to the same purpose, to read it out to blind or visually impaired people. Since then, the technology has been continuously worked on and improved and expanded in purpose. You are pretty likely to have encountered OCR technology in an everyday context. For example, when scanning a check at the bank, or when you were caught speeding and a photo of your car's license plate was taken and recognized with OCR. The level of accuracy the technology has achieved in recent years is not just due to improvement of OCR. Rather, it has been made possible by exogenous developments, such as massively increased computing capacity and the wide availability of digitized texts online. The most important factor, however, was the arrival of machine learning, the latest advancement of artificial intelligence.
Before machine learning, OCR relied on so-called rule-based computing. This means that an algorithm had knowledge of a set of letter shapes and would try and match the characters encountered on a scanned page with those different letters. The algorithm would be furnished with an alphabet library and a language-specific dictionary to help with the recognition. This would also mean that slightly aberrant fonts or irregularities in spelling would pose a significant challenge to these rule-based approaches to OCR. The technology struggled in particular with fringe cases like historic printed and handwritten books. Machine learning, however, opens up a new avenue to text recognition. Here, the software is not informed with rules, fonts, or dictionaries, but the machine trains itself to recognize letters when presented with a large amount of annotated training material. Neural networks are better at dealing with the imperfections and fuzziness of the real world because, differently from rule-based computing, they have the power to make informed guesses, like an artificial intuition more than intelligence. This intuition, however, can only be as good as the depth and breadth of the training material it is presented with. Ideally, therefore, the model has been trained on material with appropriate mass and diversity reflecting the real world through many instances, rather than one ideal type. Neural networks in computing derive their name from their similarity to the neurons working in the human brain. A modern neural network is a network of many layers, with gates that make yes-no decisions on the interpretation of an input they are presented with. These decisions are weighted by probability. In the case of OCR software, images of text lines are fed into a trained neural network, and the transcription with the highest aggregate probability is returned. Typically, these text images are presented in binarized form, that is, just black and white images. The transcriptions are simple lines of text. In the training process, the neural network is presented with a lot of this training material, then cross-checks the accuracy of its current best transcription with the ground truth. Repeating this process over and over, the gates and the probability weights are adjusted until the neural network achieves the highest accuracy with the highest probability in response to the training material. The output of this training process is a so-called OCR model, and is typically trained on hundreds of thousands of lines of ground truth. When running an OCR process on digitized images, this model is the key to the recognition process. While this may all sound rather improbable, the combination of modern algorithms, compute power, and the large training sets really do make such a system highly effective, consistently beating the best human-written rule-based algorithms in many areas. The power of a neural network compared to an algorithmic rulebook with regards to certain types of information is actually not hard to understand when we look at it from the point of human experience. It might be easy enough for you to recognize the letter A, but difficult to exactly describe how and why you recognize it. The sociologist Michael Polanyi calls this tacit knowledge, a type of knowledge you can actualize but not put into words. This tacit knowledge is what you can imbue a neural network with, without having to explain, explicitly, what the letter A looks like. Moreover, neural networks not only recognize known letters, but learn to make educated guesses on characters they haven't seen before. This is obviously a great advantage over a system where every possible instance would have to be hard-coded in advance. This also means that the decision-making of a neural network is of considerably greater complexity than a rule-based algorithm, and can also react to greater complexity in the real world, such as aberrations in letters or discoloration on the page. The downside, potentially, is that the complexity of the model is its power, but also makes it harder to analyze and fix mistakes when something goes wrong in the output. The only way to fix a model, generally, is to retrain it. There are many ways of setting up a neural network, and the one that tends to be used for OCR is called LSTM, which stands for Long Short-Term Memory. This brilliantly counterintuitive term refers to the structure of the network being able to refer to features that occurred some time before the section that is being worked on that moment. This capacity can significantly improve recognition. Being able to focus on details without losing sight of the forest for the trees is not easy, and LSTM networks have proved best at this for jobs like OCR. Rather than trying to split a text line into individual characters, as traditional rule-based OCR tended to do, LSTM network-based engines can instead split the line into 1 pixel-wide strips, feeding each into the network in order. The LSTM network can then associate as many previous strips as necessary to determine each character. The memory for an LSTM network, for OCR therefore, helps for recognizing all the markings for the individual character. It can also see further back into the line to find more context to help the recognition along. In this way, it can consign idiosyncrasies of a language to its long short-term memory when trained on the respective material. For example, it might know that an E is more likely than a C after an R letter in English, or the probability of the sequence SCH in German. A neural network fed on French text only will naturally have a French bias, therefore, not because it has an alphabet or a dictionary, but because of the material it has viewed. This also means that if you use an English OCR model for a French text, it can work reasonably well, but it is likely to not always correctly understand idiosyncrasies in French spelling, or even mistake French words for similar English ones. Thus, even though machine learning models are not a priori primed on linguistic rules, they acquire their bias through the training material. Depending on the use case, these training processes can be done with millions of words for more general use cases, or smaller, more specialized fonts, and even medieval manuscripts. The system will invariably have a bias towards the material it is presented with, so a level of diversity within the ground truth helps to prepare the model for less common cases. Too much diversity, however, means it can't work that well either. The trick is to find the fine line between.
Our course is designed to teach you how to use the open source software Tesseract. Why do we like open source software? Firstly, there are ideological factors. It is a community-oriented effort and built to benefit everyone, and everyone can feed back into it. Anyone can report errors and bugs and suggest improvements. Most importantly, it can be freely changed and adapted to specific purposes. For our work, we have used Tesseract specifically for adapting OCR to historic printed text and even medieval manuscripts written in Caroline minuscule. These models are freely available on our website, and we'll use them as examples in our course, assuming many scholars will be interested in OCRing historic texts. Tesseract itself was initially a development by Hewlett-Packard in the 1980s. It is now maintained by Google and available open source. It is highly effective OCR software and has the great advantage that it is continuously being maintained and developed further by people and organizations from all over the world. Tesseract made the transition from rule-based to neural network OCR with version 4 in 2016. It has many modern language models available which you can freely download, and it is possible to train bespoke models with a bit of know-how. Most of the normal models are trained on modern-day fonts. At Rescribe, however, we have trained a model to specifically recognize historic printing from approximately 1500 to 1800, including the recognition of special glyphs and abbreviations inherited from the manuscript tradition, for example the long S, different glyphs, and even the zodiac signs. If Tesseract is so useful and OCR is so great, why isn't everyone using it then? The answer is, you probably have been using it, or at least benefiting from it, without noticing. An open source software can be freely integrated into other programs, and oftentimes it is. Tesseract makes the books on Google Books searchable, for example. Not always perfectly, but often this helps to surface content you can search for in a simple Google search. In our course here, we want to teach you not just to use it by accident, but in a targeted manner on your own computer. Most people who do not have a moderate level of experience with the command line might have difficulties downloading, installing, and running the program. This is not because the steps themselves are prohibitively difficult. It is more a matter of the documentation being hard to understand for somebody not familiar with that type of language. This is precisely the problem we would like to solve in the next sections of this course, where we will teach you step by step the basics of using the command line, downloading and using Tesseract, and all the rest. As we've said before, if you want to spend as little time learning about this topic as possible, we recommend watching the next module, the introduction to the command line, and then skipping to the last bit, where we show you how to download and use the open source OCR solution that we built at Rescribe. If you can spare the time, we would recommend watching the full series in this course.